Hello and welcome. Well, hopefully you've had a chance to watch our previous video describing some of the foundational building blocks of geometry, namely points, lines, planes, and angles. Today we're going to be extending those building blocks into describing some foundational and important shapes that exist prolifically throughout our world. I think you'll find that today we'll be able to fulfill the promise that I made in the previous video, namely that you're going to be getting some highly useful skills that can be applied not only in applications of engineering and science, but also in terms of architecture and art. But first, let's take some time for ourselves to quiet our minds, to unplug from any additional electronic devices so that we can fully be focused on our time together. Let's take some time for that. Welcome back. Well, much of what we're going to be focusing on today are some class of shapes that we call quadrilaterals. Quadrilaterals are shapes that have four sides to them. It's as simple as that. The prefix quad indicates four. A quadruped, for example, is an animal that has four legs, 4 feet. So quad specifically means four, and we're dealing with classes of four-sided figures, four-sided shapes here. One kind of quadrilateral that we are looking at here is something called a parallelogram. I'm showing you an example of a parallelogram up here, and as you can see, it has two pairs of parallel sides that are opposite to one another. In addition to being parallel, it's also true that each one of those pairs of opposite sides are also congruent to each other. In other words, they are the same length. Some other important shapes to keep in mind. A rectangle is simply defined as a parallelogram with 4 right angles. So a rectangle is a parallelogram. It meets the definition of a parallelogram in that its opposite sides are parallel to one another and its opposite sides are equal to one another. But the rectangle has an additional qualification added to it, namely that all 4 of its angles are right angles. Lastly, we have a square, which is a rectangle that has sides of equal length. So squares are rectangles. A square meets all of the requirements of a rectangle. It is a parallelogram. Its opposite sides are parallel. Its opposite sides are congruent. It has 4 right angles, just like a rectangle. And in this case, it has one additional feature, which is that all 4 of its sides are congruent. All 4 of its sides are of equal length. There's another figure to keep in mind here. We call this a rhombus. You can think of this as a square that's been tilted on its side so that it no longer necessarily has right angles. Is a square a rhombus? The answer is yes, it is. A rhombus is simply a parallelogram with equal sides. A square meets those qualifications. It is a parallelogram and it does have equal sides to it. The rhombus simply does not necessarily have 4 right angles, as you can see there. Lastly, we have a trapezoid. A trapezoid is something, a quadrilateral that has 1 pair of parallel sides and 1 pair of sides that are not parallel. Here's the first concept to consider. These things pop up. There are two things that are going to be popping up here. One is perimeter and the other is area. For perimeter, we might be faced, for example, with this. This might be someone's backyard, and it's shaped in the way that I'm showing here, and perhaps we're wanting to build a fence around this particular shaped yard. Well, how do we calculate how much fencing we need to purchase in order to be able to place this fence around this yard? Well, we have 4 different sides to this trapezoid labeled A, B, C, and D, and simply all we have to do to find the perimeter is to add all of those sides up. Perimeter means distance around. Peri means around. Meter means measure. We measure around the particular figure that we've got here. And in the same way, we would do the exact same thing for each one of these quadrilateral shapes, starting with a rectangle. I'll bet that you'll be able to take a look at the definition of perimeter and perhaps be able to think up a more refined way, a more refined formula, if you will, for describing the perimeter of a rectangle. Perhaps you're noticing that it's got 2 lengths and 2 widths. So it would be 1 width plus 1 width plus 1 length plus 1 length, or perhaps in a more simplified form we might say 2 lengths and 2 widths. Precisely. The formula for a perimeter of a rectangle is 2L plus 2W, where L and W describe the length and the width of the rectangle. You could memorize this formula, or you can just understand it so that you can call it up within your mathematical intuition whenever you need it. In the same way here, how could we apply this same concept of perimeter to the square? Well, in this instance, we are adding up 4 different sides labeled S, and all of these sides have the same length. So in this case, our perimeter is just 4 times S. And if we take a look at a rhombus, as it turns out, it's the same thing. We have 4 equal sides that we're adding up, and we get a similar formula. P for perimeter equals 4 times S. What's the perimeter of a triangle? Well, it's pretty much the same thing here. We have 3 sides instead of 4, so this is not a quadrilateral. This is a triangle. So we've got 3 sides to add up here, and as you might guess, perimeter for a triangle is simply A plus B plus C. We have a special term for perimeter of a circle. We use the term, not perimeter, we use the term circumference. And you might be aware from some popular discussions of this, but there are 2 ways in which we can calculate the circumference of a circle. The first is by taking the diameter of the circle, that's the distance across the circle going through the center, and simply multiply that by the number pi. That's that 3.1415926 5 and so on number. It's an irrational number. It goes on forever without any pattern whatsoever, but that's the number that you multiply the diameter by in order to get the distance around the circle, the circumference of a circle. For example, if this, and that's actually what defines what pi is. Pi is the number that you would get if, for example, you measured using a tape measure, a flexible tape measure, the distance around one of your dinner plates or one of your the car tires, and measured the distance around, got a value there, then measured the distance across going through the center and divided the first number by the second, you'd get pi. There's another way in which we can describe the circumference around the circle, not using diameter but using radius. You can probably tell from that diagram up there that the radius just extends from the center out to one point on the circle, and you can probably discern that the radius there is half the size of the diameter. That diameter is really composed of 2 radii that are added together. One goes from one side of the circle to the center, the second one goes from the center to the opposite side. 2 radii added together. So if we're dealing here with not a diameter but a radius, now it's pretty much the same idea here, but we can say 2 pi r. All right, so that's really the same thing as pi times diameter. It's pi times 2 radii, because that's what a diameter is. It's 2 radii added together. So 2 pi r is another equivalent formula that we have for finding the circumference of a circle. So, for example, let's find the perimeter of this rectangle here. Now, it looks easy at first, but in kind of a sneaky fashion, I've made those two measurements there of different units. The 6 there is actually 6 feet. The 9 up on top is actually 9 inches. Those are two separate units there that we have to find a way to convert between. But the formula is still the same here. We are using 2 lengths plus 2 widths, so that's 2 times 6 feet plus 2 times 9 inches. So we're going to get 12 feet plus 8 inches. Let's convert as many of the inches as we possibly can into additional feet. There are 12 inches in a foot, so we can get one more foot out of those 18 inches there. So 18 inches is 1 foot plus another 6 inches. So we've extracted another foot out of those 18 inches for a total of 13 feet, 6 inches. That is the perimeter of that rectangle. What's the perimeter of this triangle here? Well, once again, I'm showing feet and inches. This might be confusing considering that in a previous video I showed an apostrophe and 2 apostrophes showing minutes and seconds, the way that we might define a measurement of a degree, of an angle rather. In this case, 1 apostrophe and 2 apostrophes, these are measuring a distance of a line across a line segment. This is showing feet and inches. So we have 3 different measurements for these 3 different sides of the triangle. We have 4 feet 5 inches, that's one side. Another side is 3 feet 6 inches, and the third one is 2 feet 8 inches. Well, let's see how we would add all of those together. We would first of all do that, obviously, in order to get our perimeter. Well, if we add up all the feet, we get 3 feet plus 4 feet plus 2 feet. 3 plus 4 plus 2 is 9. All right, so that's 9 feet. And let's add up all the inches here. 6 plus 5 is 11, plus 8 is 19 inches. So what we have initially is 9 feet, 19 inches. And just like before, we can extract another foot out of those 19 inches there and write this in a more in a simplified form as 10 feet, 7 inches. So take some time to do these things. Here I'm showing you a square in which the length of each side is 4 feet 3 inches, and I'm showing you a rectangle here that has one side that's 3 yards and the other side is 2 feet. By the way, there are 3 feet in each yard, 3 feet in each yard, so that's how you're going to convert from one to the other. So take some time to calculate the perimeters of those 2 quadrilaterals. Welcome back. Well, the work that's on your paper might look a little different than the work that I'm showing here on the screen. It's a lot of stuff that I'm showing. My desire here is to show all the possible work that you might be showing on your paper as you're doing all these calculations together. For the square, we have 4 sides, each one being 4 feet 3 inches there, so you can see that as the first term over there. That's 4 times 4 feet plus 4 times 3 inches. All right, well, 4 plus 4 feet is 16 feet. 4 times 3 inches is 12 inches. 12 inches is just 1 more foot, so we have 16 feet plus 1 more foot for a total of 17 feet. That's the perimeter of that square there. Secondly, we have the perimeter of the rectangle here, so we've got 2 lengths and 2 widths. So we have 2 of those 3 yards, and we have 2 of those 2 feet. 2 of those 2 feet, I should say. And for each one of those, so what we have a total there is 6 yards plus another 4 feet. 6 yards, 3 feet in a yard, that's 18 feet, plus another 4 feet is simply 22 feet. Now if you want to convert it back to yards and feet, it might be 7 yards, 1 foot, or even 7 1/3 yards. Different ways to say the same quantity here. Here's another one. The rear window of a pickup truck is a trapezoid whose shorter base is 40 inches, whose longer base is 48 inches, and whose non-parallel sides are each 16 inches. Let's take a moment to visualize that. So we've got 2 bases to this trapezoid here. We've got one on top and we've got one on bottom. These are the parts of the quadrilateral that are going to be parallel to one another, and then we have these other 2 sides here. I'm picturing this as a window on the back of a pickup truck here, and so yeah, as you can tell, these sides here are not parallel to one another, and so it looks like those non-parallel sides are each 16 inches. So this is a window that has the shape of a trapezoid. It is 40 inches on top, 16 inches on each of these sides, and 48 inches on the bottom. And we are placing some rubber gasket around this particular window, and we're asking how much is necessary in order to surround the window. Well, that's another perimeter problem, isn't it? So take some time to calculate what that would be. Welcome back. Well, hopefully this was pretty straightforward here. We have 4 different sides of a quadrilateral that we are adding together in order to get the perimeter here. 40 inches plus 48 inches plus 16 plus 16 for a total of 120 inches or 10 feet. Perhaps you described it that way. 10 feet is the same thing as 120 inches. Here's another problem. This is a triangular gable that's being used to support the roof of an apartment unit, and we are going to be outlining all 3 sides in some contrasting trim. So around the edges of all 3 of these sides, they're going to be placing some contrasting trim, most likely decorative in nature, to cover all 3 of those sides there. So if each gable is 32 feet wide, as you can see there, and 18 feet on each side, how many feet of contrasting wood trim are needed for each gable? It should say for each gable. Disregard overlap at the corners. So in other words, let's not worry about how much more we'd have to overlap because there's a layer of trim that's coming off the one competing side here and it has to be overlapped on the other one. Anyway, let's just not deal with that. So it is basically the length of each one of those sides, so let's find the perimeter of that triangle. Take some time for that. Welcome back. Well, it looks like I'm having a few technical issues here. We should still be seeing that picture of the triangle in place of another copy of that equation showing our calculation here. In addition, this should be in feet, not inches here. 32 feet plus 18 feet plus 18 feet should be 68 feet. Now let's actually have some fun with this as well here. This is a kind of a complex shape that we want to eventually calculate the perimeter of, but in this case not all of the side lengths are provided. You can see there's an X and a Y, so some of those lengths are unknown. You can assume with this kind of a figure that I'm giving you that all of the angles are right angles, and so based upon that assumption, ask yourself, how can I figure out what the lengths of those two sides are, X and Y? So take some time to do that. Welcome back. Well, the point of this exercise was to illustrate how you can sometimes find the length of a missing side by taking the length of a longer side and subtracting a shorter side. Take a look at this example here. There's a very long wall on the left-hand side that is 8 feet 6 inches long. And so a way in which we can find the length of X is to take 8 feet 6 inches and subtract off the length of that wall on the far right, which is 3 feet 6 inches. If I subtract the length of that wall by the length of the from the length of the larger wall, 8 feet 6 inches, then I should get the length of X. So you can see the calculation there on the left. 8 feet 6 inches minus 3 feet 6 inches is simply 5 feet. In a similar fashion, how can we find the length of Y? Well, it has an opposite wall that is very long. It's 12 feet 6 inches, and that opposite wall is opposite not just y, but also this other rear wall that is 5 feet 6 inches. So 5 feet 6 inches plus y should be the length of that opposite wall of 12 feet 6 inches. Which means that the way that we find the length of y is to simply take 12 feet 6 inches and subtract off 5 feet 6 inches. And you can see we're doing that on the left-hand side there, and we get 7 feet for y. So that's just an exercise there to kind of get you ready for this kind of problem here. So let's find the perimeter of this shape here. You're going to see that you have to calculate some missing measurements on 2 missing sides in order to do that. So take some time to find those missing measurements and also calculate the full perimeter of this object. Welcome back. Well, finding the lengths of x and y were hopefully pretty straightforward there. To find the length of x, we took the opposite wall length of 15 feet and subtracted off 7 feet on an additional wall next to, well, close to x, and we got a length of 8 feet. Similarly, in order to find the length of y, we took the length of the opposite wall, 24 feet, and subtracted off 9 feet, which is another wall that's parallel to y. The result there was 15 feet. So we have all 1, 2, 3, 4, 5, 6 sides that need to be added together in order to get our perimeter. The result is 78 feet. All right, so now's our chance to make use of some additional formulae that we've covered and that you've learned. How do we find the circumference of a circle? Well, we had 2 different formulae that we made use of. One was pi times the diameter. The other was 2 pi r, where r was the radius. In this case, that's what we have. We have a radius of 1.6 meters. So let's plug that in to our formula here. Circumference equals 2 pi r, so we have 2 times 3.14, that's the approximation that we're going to be using for pi in this example here, and we'll multiply that times 1.6 meters. The result that we get is 10.048 meters, so just a little bit over 10 meters, the distance around that circle. So make use of the same kinds of formulas. You won't be using necessarily 2 pi r in order to be able to calculate this circumference, although you might use it. But find the circumference of this circle, and in this case use 22/7 for pi. That's another popular approximation for pi. It's the one the ancient Egyptians used. It actually works pretty well. I think to about 2 decimal places. That's pretty good figuring for 3,000 years ago. So take some time to find the circumference of this circle using those measurements. Welcome back. Well, in this case, you could have used the same formula as before, the 2 pi r formula. Just remember that the radius is 1/2 of that diameter, so for a radius you're using not 14 centimeters, but 7 centimeters. Putting that into 2 pi r, you'd have 22/7 times 14 for 44 centimeters. You can also make use of the perhaps more convenient formula, which is simply pi times diameter, or 22/7 times 14, to give us, again, 44 centimeters. Let's talk about area here, and I've got an example here of a closet that is 6 feet by 4 feet, and I want to ask you something. I want you to visualize some of those 1-foot carpet squares that you can sometimes purchase at hardware stores or carpet outlet malls or things like that, places like Home Depot or Lowe's. And that's oftentimes a way in which carpet is laid down into new locations. And so let me ask you, if one side of this closet is 6 feet long and another side is 4 feet long, then how many of those carpet squares am I going to have to lay down in order to cover this entire closet in carpeting? Well, let's hopefully make use of this hopefully helpful visual image here of a single row on top of 6 of those carpet squares, and then 3 more rows of the same thing. 4 rows of 6 carpet squares, 4 times 6, 24 square feet. The way in which we find the area of a rectangle is multiplying length times width. In the same way, what's the formula that we might use if we were finding the area of a square? In this case, length times width. Well, the length and the width are the same number, represented by s. So this is now s times s, or s squared. Similarly, how do we figure out the area of a parallelogram? Well, it's pretty hard to visualize placing carpet squares inside a figure like this and coming up with some measure of area on the inside of this. But here's something that we can do. I want you to visualize here that I'm cutting off a part of this parallelogram here, a part that starts in the upper left-hand corner and goes downward to the opposite side, ending at a right angle. And what I do is I cut off that purple triangle to the far left, and I move that triangle to the opposite side of the parallelogram. So we've transformed this parallelogram into hopefully a more familiar shape, namely a rectangle. We can see here that we can calculate the area of this parallelogram by calculating the area of a same size rectangle here. Well, it's length times width for a rectangle. What is the length? Well, it's one of those bases. The base I want you to think of as being either the top side or the bottom side here. It's the side that the quadrilateral sits on, so to speak. So it's the length of that base times, well, a new dimension. It's not really the length of that diagonal side, is it? It's something different. It's the thickness of the parallelogram, which we might also define as the height of the parallelogram. It is the length of the perpendicular distance from one base to the opposite base. So we call that the height, and we say that the area of a parallelogram is simply base times height. And you can define base times height in any way that you desire here. All I've done is I've taken this same parallelogram and I've placed it on its other side here. Well, the base is a little different here. It's this small side that it's sitting on here, and the height is going to be something different as well. It's going to be the thickness of this parallelogram. It's going to be different from the height before. The point simply is that regardless of which side you tip the parallelogram, you're going to get the same answer here. And in all cases, it's always base times height. So So let's calculate the area of this field here. We've got a parallelogram-shaped field. It's actually pretty large. It's 3 kilometers on an opposite side there, the far side. Its base that it's sitting on here is 2 kilometers, and we have this perpendicular distance here of 2.8 kilometers. So calculate the area of this field. We find base times height. Well, what is the base? That's the 2 kilometers that's sitting on the bottom there. And the height, is that the 3 kilometers to the far left, or is it the 2.8 kilometers that represents that perpendicular distance? Well, hopefully you remember that that's the 2.8 kilometers that is the perpendicular distance. So we don't actually use that 3 kilometers on the far side over there. The result is 5.6 square kilometers. Perhaps you're noticing here that in describing area, we're not using our previous perimeter units of feet, inches, miles, and so forth. We're now using a different kind of unit, a square unit. These are not kilometers, these are square kilometers. These are not feet, these are square feet. A square that is a foot on each side here. So we have units of area that we're working with, not units of length any longer. So we have to define this in terms of square, in this case, square kilometers. And the way that we write square kilometers, we could actually say SQ and then kilometers. That's one way to do it. The other way we can do it is to say kilometers with a little squared sitting above it as well. That's another way in which we do it. It's actually a more shorthand way of saying square kilometers. So take some time to find the area of this parallelogram here. Hopefully this will be pretty straightforward. Welcome back. The area of a parallelogram is base times height, and you are given both the base and the height in this example here, 10.4 inches times 3.1 inches for an answer of 32.24 square inches. And you can see square inches being abbreviated there in a similar fashion to kilometers, square kilometers in the previous slide, and square feet in some slides before that. Well, how would we calculate, for example, the area that is in this white matting of this particular painting here? I'm showing you a painting that is in the center of this frame here, and there's some white matting that exists around it, and on the outer portion of there's a frame. Well, what's the area just of this white matting that exists here? Well, there's an easy way to figure this out, and there's a hard way to figure this out. The hard way would be to try and divide that white matting into sections and to say, well, here's a rectangle, here's a rectangle, here's a rectangle, the area of this part is this, the area of that part is this. That's one way to do it, but it's the more difficult way of doing it. The easier way to do it is to take the large rectangle showing basically around the frame and just subtract the picture that's in the center there. We take the large rectangle and subtract the smaller rectangle. Let me show you what I mean here. So the big rectangle minus the small rectangle means that we take the area of the first rectangle, that's the 20 inches on top and the 16 inches closest to me here. That's the area of the biggest rectangle, and the area of the smaller rectangle in the center there is the 16 inches near the bottom and the 12 inches in the far left there. Those two multiplied give us the size of that smaller rectangle. If I subtract that off of the larger rectangle, then I get the area of the matting, the area that's left over, 128 square inches. So in a similar fashion, do this problem here. It's a side of a house that has to be painted. We want to paint the entire wall, but we don't want to paint those windows. So estimate the total amount of area that's going to be painted. Take some time for that. Welcome back. Well, this involved finding the area of a large rectangle and subtracting off some smaller rectangles, just like before. The area of the entire wall there is 12 feet by 40 feet for a total of 480 square feet. Each window there is 4 feet by 4 feet, so 16 square feet, and there are 2 of them, so we have to subtract off 2 of them. So we have 480 square feet minus 16 square feet minus 16 square feet for a result of 448 square feet. Let's talk about how we calculate the area of a trapezoid here. Now, if you recall the area for a parallelogram, it was base times height. And so we have a base on the bottom. It's also the same size as the base on the top. As you recall, for a parallelogram, opposite sides are the same size. In this case, we have a trapezoid in which we have a pair of sides that are parallel, but they're not the same size. The one on the bottom in this case is larger than the one that's on the top. So we actually have 2 bases being shown here. We have and I've labeled them B1 on top and B2 on the bottom. There's still a height that we are showing here from the bottom side to the upper side there. It's defined in the same way as it is for a parallelogram. And actually our formula is pretty similar to that of a parallelogram. As it turns out, what we do is we take the lengths of those 2 bases and we average them. What does that mean? Well, we add those 2 lengths together and we divide by 2. As it turns out, when we take that average of those 2 bases and then multiply that by the height, base times height, we get the area of a trapezoid. Exactly, the area of a trapezoid. It works. So if we have, for example, this trapezoid, which has a side on the top that is 6 inches, side on the bottom is 8 inches, it has a height of 4 inches, we can calculate the average of those 2 bases, 6 inches and 8 inches, by plugging it into the formula here. 6 plus 8 is 14. So we've added those together. Now we divide by 2. 14 divided by 2 is 7 inches. 7 inches is the average of those 2 bases there. You can perhaps see that more intuitively here. 6 inches on top, 8 inches on bottom. What's in between those 2 lengths? Well, it's 7 inches. That's the average of those 2 lengths. All right, so 7 inches times the height, which is 4 inches. 7 times 4 is 28 inches. So it's actually 28 square inches. We've calculated the area of this trapezoid. In similar fashion, I'm giving you another trapezoid here to find the area of that. Take some time to do that. Welcome back. Well, once again, we're finding the average of two bases, the top one and the bottom one, and we're multiplying that average times the height. Base 1 and base 2 are 11 centimeters and 15 centimeters, so when we average those two together, we get 13 centimeters. We multiply that times the height of 6 centimeters to get us 78 square centimeters. Let's talk about how we find the area of a triangle. And some of you might know already from some statements in popular culture that the area of a triangle is 1/2 base times height. You're about to find out why that's the case. And as it turns out, it has to do with a connection that triangles can have to parallelograms. What I want to do is take this triangle here and make another copy of this triangle. I think I'll make it purple again. And I'll make a copy of this and turn it upside down and place it on top of our first triangle. So you can see that there. Those two triangles are the same, just one is upside down, placed on top. Well, putting these two triangles together, what kind of shape have we created? You can see, obviously, that this is a parallelogram, and we know how to find the area of a parallelogram. It is base times height. In the same way, we now know that the triangle being half of a parallelogram will have an area 1/2 of base times height. Now we can, just like with the parallelogram, you can turn it on different sides and see a base and a height. They're usually different depending on how you turn it, but you'll get the same answer once again, regardless of how you turn the figure. You can see here actually that in this case we have an obtuse triangle. That means a triangle that has one obtuse angle. You can see the one that it's causing it to bend back just a little bit here. That's an obtuse angle, so we call this an obtuse triangle. And you can see here that the base is a rather small side, and that the height is actually a little bit strange there, in that it's actually pulled off. But once again, this is 1/2 of a parallelogram. Just like before, this is 1/2 base times height. So we have three different ways of looking at this, because there's three different ways in which you can orient the triangle depending upon which side you rest it on to make that side the base. If we make this first side the base, then you can see that the height goes up to that opposite point there. So that's one measure of base times height. We can turn the triangle on another one of its sides. I'm rotating it clockwise there, so that that smallest side is now the side that it's sitting on. So we have a different base and a different height. It doesn't look like we should get the same answer when we take 1/2 of multiplying those two things together, but as it turns out, we do. And then lastly, we rotate it clockwise again, so now it's sitting on that third side. We have a different base and a different height again altogether. But once again, it doesn't matter which base and height you choose. In other words, which side you have the triangle sitting on when you assign a base and a height. You'll get the same answer regardless. Also true for this strange obtuse triangle that I showed you before. We can rest it on that short side and have that side as the base, and this is the height. We can rotate it clockwise to have it sitting on that somewhat larger side there, so we have a somewhat larger base and a somewhat smaller height. So you can kind of see how they interplay with one another. When the base gets a little bigger, the height gets a little bit smaller, and vice versa. We can then rotate the triangle once again onto its longest side, so we have a very long base, and not surprisingly, we now have a very small height to multiply it by. Either way, we're going to be calculating the area as 1/2 base times height. So when you're taking a look at a triangle, sometimes you'll get different measurements in different orientations, and you'll have to turn the triangle in your mind to see, okay, which side am I using as the base and which perpendicular distance am I using as the height. Let me show you what I mean here. You might see the triangle this way, in which it's sitting on the base and the height is that up and down distance that you're seeing there labeled with h. But you might also see this triangle displayed not with that stuff in black, but this stuff in red here, in which case the base is that far left side there. So you have to imagine turning this triangle onto that side, having it sit on that side as the base, in which case that red line is now the height. In other words, if that triangle were to be sitting on that side as the base, its height would now be the length of that red line, wouldn't it? Lastly, you could place the triangle on this side nearer to me, that is labeled with a green B. If we set the triangle down on that side, we would have that side as a base, and the height would be something different altogether once again. So you might see a triangle labeled with any one of those configurations of base times height, and you have to be able to rotate the triangle in your mind in order to be able to see, okay, I'm going to use this measurement as the base and this measurement as the height. 1/2 base times height, I've got the area of the triangle. So here's an example here. What's the area of that triangle? Here are some things that I'm showing you more information than what you need to have. What's the information that you need? What's the information that you don't need here? Well, the base in this case is that bottom side, 3 inches. The height is that dotted line, which is 4 inches. There are 2 measurements that you don't need, the 5.5 inches of that far side and the 5.6 inches that's nearer to us. So 1/2 base times height in this case is 1/2 times 3 times 4, which is going to be 6 square inches. Here's another example. I'm showing you here another triangle, and I'm showing you the length of one of those sides there. It's kind of a small length. It's that smallest side there. And that's measured at 4.4 centimeters. And then I'm showing you all these dotted lines here, and I'm showing you one that's nearest to me here, which is 7.8 centimeters. Where's the base and where's the height? Well, in this case, you have to visualize that triangle being set down onto that smallest side, that side that's only 4.4 centimeters. Imagine that triangle being placed down on that side, so that that side's on the bottom, 4.4 centimeters. Okay, that's our base. What's the height? Well, the height of that triangle is now going to be this length of 7.8 centimeters. So we now have our base and we have our height. So the area of this triangle, we plug in those things into the equation. Again, we get 17.16 square centimeters. So take some time and find the area of this triangle here. You can see 2 measurements listed there. Find the area of the triangle. Welcome back. Well, hopefully this was pretty straightforward here. You can see that if we were to place the triangle on that longest side there, that side that's 7 meters long, if we placed it on top so that it's resting on that side there, that 4-meter measurement there would be the height of that triangle. We have for the measurement of area, we have a base and we have a height, so we can calculate the area of the triangle, 1/2 base times height, or 14 square meters. Let's also take some time to find the area of this large object. There's a bunch of different ways in which you can do this, actually, but take some time to do this. Perhaps it's a divide and conquer approach, perhaps it's the large rectangle minus a smaller area, so on and so forth. Figure out a way to do it yourself that's perhaps all your own, but take some time to calculate the area of this large figure. Again, you can assume that the angles are right angles as you do so. Welcome back. Well, this is one of many ways in which you could have calculated the area of this figure here. What I did is I divided it up into 2 rectangles, a smaller one to the left and a larger one to the right. You could have just as easily taken the area of the large rectangle, in other words 24 feet on the bottom times 15 feet on the side, and then subtracted off the part that's cut off, the smaller angle that's taken out, the smaller rectangle, I should say, that's taken out of the upper left there, the rectangle that would be 9 feet by 8 feet. If you subtract off that bite that's being taken out of the larger rectangle, then you could calculate the area that way. But here's the way in which it was done here. So the first rectangle is 7 feet by 9 feet, and that's 63 square feet. The second one is 15 feet by 15 feet, that's 225 square feet. When we add those two together, we get 288 square feet. Here's another example of an area problem that really involves dividing the figure into 2 different parts here. This is an area of a gambrel roof that has dimensions like this. You can actually think of this as 2 shapes in one, a triangle on top and a trapezoid on bottom. You can consult your formulas for calculating the areas on both of those things, but take some time to calculate the full area of the gable end of this gambrel roof. Welcome back. Well, this is an example of dividing and conquering, so to speak. You've got two shapes there, a triangle and a trapezoid, and it's a process of calculating the areas of each one of those portions and adding them together. First, with the triangle, we have a base of 23 feet, and we have a height of 5 feet 4 inches. We can keep it in feet and inches if we want. We can convert everything to inches if we want, or we can take 4 inches and describe that as a fraction of a foot. 4 inches is 1/3 of a foot, so we can describe 5 feet 4 inches as simply 5 1/3 feet. And so we do. 1/2 base times height becomes 61 1/3 square feet. That's the area of that upper triangle. Secondly, we have a trapezoid. The area of that trapezoid involves finding the average of the top and bottom bases. You can see there that the top base is going to be 23 feet, but when we take a look at the bottom base, we add 3 feet on one side and 3 feet on the other side for a total of 29 feet. So 23 feet on top, 29 feet on bottom. We find the average of those two bases and then multiply that by the height, which for the trapezoid is 8 feet. The result that we get is 208 square feet. That's the area of the trapezoid. And if we add those two portions together, we get a total of 269 1/3 square feet. Let's move on to the area of a circle here. This is another one that you might have heard in terms of popular vernacular here. The area of a circle is pi r squared. This involves specifically the radius, not the diameter here. It's the radius squared multiplied by pi. Now it's important to keep in mind here when you're doing this using your calculator that you do the exponent part first here. So find out what the radius is. If the radius is 5.5 inches, so to speak, then take 5.5, square that first, then multiply it by pi. So you're going to be working a little bit from right to left, but it's necessary in order to preserve order of operations here. We do the exponents first, then the multiplication. So make sure that's how you're doing it on your calculator here. If we want to take some time to understand why the answer is pi r squared, I want you to take a look at this circle in the upper left-hand corner here, and I'm taking slices out of it that are respectively blue and yellow in color, and then what I'm doing is I'm placing them side by side, sort of facing each other, sliding into each other as separate almost triangular shapes there, into what actually looks a little bit like a parallelogram. As you can see, it's got a base on the bottom, and that base has the length of pi times a radius, in that it's the distance across all of those blue sections of the pi, as you can see along the top there. So if we just were taking a look at the blue portions of that circle there, that would not be 2 pi r, that would just be pi r. The blue sections are just half of the circle, so the distance around the blue parts of that circle would be half the distance around the circle. So that's not 2 pi r, it's just pi r. So the base of this parallelogram here, you can see that just involves those blue segments there, those blue pies. So that's just pi r on the bottom there. And the height of this parallelogram is r. Base times height, pi r times r, pi r squared is our formula for the area of a circle. And it comes from splitting off those pieces and making it look a lot like a parallelogram here. You can see that illustrated. All right, so here's an example here involving an 1831 coin from the United Kingdom. It's 3.32 centimeters in diameter. Let's find its area using 3.14 as an approximation for pi. Let's round our answer to the nearest hundredth, so 2 decimal places here. Okay, so our formula here is simply pi r squared, so we have to take the diameter, watch this, this is important, 3.32 is our diameter, not radius. The radius is half the size of that diameter, so we have to cut that in half. It's not 3.32 squared, it is 1.66 squared. So 1.66, we square that on the calculator, then multiply that by 3.14, and we should have our area. It's about 8.65 square centimeters. So do this one on your own here. This is a 9-inch diameter plate, so the distance across the plate through the center is 9 inches. Use 3.14 as your approximation for pi, and round your answer to the nearest tenth, so just 1 decimal place. Take some time for that. Welcome back. Well, this is a problem very similar to the one before it. We're having to take the diameter and divide it in half. Once again, it's not 9 inches for the radius, it is 4.5 inches for the radius. So we have to square that to get the r squared, then multiply it by pi to get a rounded answer of 63.6 square inches. You might be wondering what that little squiggly equal sign means. It means approximately equal to. That's our common symbology for that. Well, here's some other ways in which we can find areas of more complex shapes through this divide and conquer methodology. Sod can be purchased in pallets for $225. If a pallet contains 240 square feet of sod, how much will it cost to cover this whole area here? Well, I'm showing you a large lawn here, which is 90 feet in width in this direction here, and it seems to have two sections to it, one that can be described as rectangular, where the distance in this direction is 40 feet, and then there is another which perhaps can be described as trapezoidal, in which we have two sides, one being 20 feet and another side being, how would we calculate the length of that dotted line there? Well, I'm thinking that it would be 90 feet from the bottom minus 30 feet from the upper left. 90 minus 30 will be 60 feet. Okay, so we have 20 feet and 60 feet. Those are the two bases of that trapezoid. And then we have the height of the trapezoid showing there as 30 feet. Okay, so once again, I'm dividing this section up into two subsections, one that's A, one that's B, and I'm calculating the area of part A as being 90 feet times 40 feet, which is 3,600 square feet. And we're once again calculating this distance here as being 90 feet minus 30 feet, or 60 feet. So we now have all of the measurements needed in order to calculate the area of this trapezoid here. 20 feet plus 60 feet divided by 2 times the height of 30 feet. So that gives us an answer there of 1,200 square feet for a total of 4,800 square feet. And the result there is that we can find out just how much it's going to cost in terms of sod. So what I'm doing is I am almost using the price per pallet there as a kind of unit conversion fraction here. So we know that $225 is the price for a pallet, and each pallet gives us 240 square feet of sod. Okay, so if we place the square feet in the denominator, we're going to be converting square feet into dollars, the dollars that are on top there. So the result there is $4,500. So let's work on this one here next. This is a more complex figure here. Once again, how in the world do we calculate that the area of that green section there? So this is a flat metal piece that's shown in the figure. It's all in green. How in the world would we calculate this? This is a good challenge problem for you. Take some time for this. Welcome back. Well, this was certainly the most complex geometric shape of the lesson for today. In this case, we are taking really there's a bunch of ways in which you could have done this. The way that I chose to do it was to divide it up into a big rectangle and a small square. The big rectangle you can think of as being Well, it might be easier to point out where the small square is. 3 centimeters by 3 centimeters, that's that small little nodule that's in the upper right portion of it. That's the small square that we calculate the area of that. And if you were to ignore that triangular cut that's made out of the bottom of this, then the rest of this figure here is the larger rectangle. The larger rectangle there is 12 centimeters by 10 centimeters, or 120 centimeters. That plus the small square is 9 square centimeters as well. Now let's talk about the area of this triangle in here, which we will subtract from that total area in order to get the area of the green portion here. Well, the area of the triangle, it takes some time to figure out because you have to infer some distances here, like the distance of this dotted line along the bottom there. That is 15 centimeters taken from the very top side, minus 5 centimeters to the left, and 3 centimeters in the upper right there. So that leaves behind 7 centimeters. That's the distance across that dotted line. And what's the height of that triangle there? It's 10 centimeters from the left-hand side minus 3 centimeters from that square in the upper right to give us 7 centimeters for the height of that triangle. So 1/2 base times height, 1/2 7 times 7, that's 24.5 square centimeters. That's the amount that we are going to subtract off from our big rectangle and small square total to give us 104.5 square centimeters. Well, that's as tough as the problems have gotten here today. So think of all the stuff that we've covered in this particular video here. We started off defining what quadrilaterals are, talking about the different kinds of quadrilaterals. We covered parallelograms, rhombuses, rectangles, squares, trapezoids. We described what the definition of perimeter is, what the definition of circumference is, and we came up with some formulas for defining what the perimeter is for some of those shapes. In addition to that, we came up with some formulas for describing the circumference of a circle. And those are actually 2 separate equations that we use 2 separate formulas for doing that. In addition to that, we really came up with some additional formulas for the area of a parallelogram, the area of a rectangle, the area of a square, the area of a circle, and finally the area of a triangle, and the area of a trapezoid as well. So we got through an awful lot of formulas today, describing a lot of separate relationships. And in addition to all this, we really described a process of divide and conquer, which allows for you to take some of these fundamental shapes and apply them to the more complex shapes that are, frankly, more commonly found in real life. So there's a lot of stuff that was covered here today. Make sure that you go through your activity sheet, circle the things that were most important so that those things are readily available to you. It's very easy to get lost in these videos in the step-by-step process and to think that you've got to copy down verbatim everything that gets done or everything that gets said, when really all that you have to do is to understand what we're doing as being variations on a set of themes. And if you get what those central themes are, then you've got the lesson. And you can move from a position of just memorizing stuff to fundamentally and more importantly understanding it. So take some time to do those summaries of the information that was in this lesson, and I'll see you in class.